So there are all sorts of different complex situations that can arise with different sets and how they might be subsets of the other, or you're looking at 3, 4, 5 different sets. And so in this last video, we are going to look at more complex versions of Venn diagrams and how they can appear. And then we'll end by looking at a real world scenario that you could use a Venn diagram to solve a problem with. So here we go. We are going to sketch a Venn diagram for the description here so that all of the given conditions are satisfied. All right. So we're going to sketch Venn diagrams. This doesn't require any shading. It's just how the circles are sort of connected or not or inside each other that really matters. Okay. So here is our condition. We are going to have 3 sets, set A, B, and C. So for number 1, set A, I'm just going to write this, and you see if you can remember what the symbols mean. So this is really, oops, I put the slash in the wrong spot. There we go. Okay, so this is incorporating a lot of the different terminology and symbols that we've used throughout all of the videos in this section. And so do you remember how we would read these symbols? Pause and give yourself a shot to try to figure it out before I say it. So it's A is a proper subset of B, and B intersect C equals the empty set. Okay, so what we're going to be doing here is we're going to be sketching, first of all, our universal set as a big rectangle. And I suggest just playing around with the different circles, drawing them inside each other, connecting outside, however you think, until you can figure out what this might look like. Take a few minutes and try to do that on your own. Then come back, pause. So I'll keep going. So you might start off with just the one on the left. A is a proper subset of B. So what might that look like? Well, we could start with B. Let's call this set B. And if A is a proper subset, that means all of A fits inside of B, and there's at least one element outside of A, right, that exists inside B. So that part of it we've got, right? A is a proper subset of B. But then I said, and this also has to be true. B intersect C is the empty set. Well, what does that mean? It means that there's another set C that if you look at the intersection point of B and C, there are no elements in there, right? So normally if we look at B and C as 2 intersecting sets, the intersection point would be here, right? But this statement says that they really have nothing in their intersection points. Well, that tells us that C is really its own separate set over here, and it's completely disconnected from B. So this diagram right here shows the information that's stated right there. We've satisfied all those conditions. All right, one more for you to try. So number 2 looks like this. And let me just double check to make sure that I wrote all that correctly. And I did. So pause the video, see if you can figure out how these sets might relate to each other in a diagram. Okay, so hopefully you've paused, you've tried this, come back, and let's find out. So this says A union B is a subset of C. So that means there's this set C, and A and B are inside set C. But there's a union going on of A and B. So maybe if we just start, we know that A and B are inside C, but before I even draw, it also says A intersect B is not equal to the empty set. So what that means is that there is an intersection point between A and B, right? Unlike the previous example, where B intersects C was the empty set. Remember how these were separate from each other? That's not the case for this one. We're going to have A and B exist here and here. And notice there's an intersection point between them, right? There's going to be something that exists that they have in common. But that the union between them, which would be all of their elements, exists as a subset of C. So A and B are inside, they intersect, they overlap, but they exist completely inside set C. All right, so we're going to end this section with a real world example. And I'm going to do a little copy and paste so you can read this. And then we're going to look at see how we can actually use different numbers here to and a Venn diagram to solve a real problem. So what this says is that a survey categorized 120 people based on their use of TV, computers, and smartphones for news access. The data includes overlaps between categories, which means that 55 people said they used a computer. Well, that also includes this group and this group, okay? So just keep that in mind. Create a Venn diagram to represent the information. So you're going to be designing a Venn diagram that shows all of this. And what that means is that every different region in your Venn diagram should have a specific number, okay? And eventually what we're going to figure out is this question. How many people did not use any of the methods stated to obtain their news? All right? So I'm going to start this for you, and then we will, then I'll let you try to finish it. So I'm going to start with our big universal set, because this involves some calculations, all right? So this is our universal set, and then we're going to have three overlapping circles. Three overlapping circles. That's not too bad. That's a pretty good drawing, I think. Three overlapping circles. Okay. And those three overlapping circles are going to represent the three modes of news gathering: TV, computer, smartphone. Okay. So I'm just going to write right next to them. We'll put TV here. I'm going to put computer over here. And I'm going to put, I'll just put phone for smartphone. Okay. So TV, computer, and phone. All right. So then what we have to do is we have to use the information up here to start to figure out how big are each of these sets. And to start, pause the video and see if you can figure some of this out on your own. Because what we eventually want is a number in each of these sections. So I'll give you a couple minutes to try that on your own first and see if you can tackle this problem-solving exercise. I'll keep going though. So the key to doing this is working inside out on your Venn diagram. Did you do that when you thought of this? This right here, computer, phone, and television, that's really the intersection point between all three of those things. Those people responded, 5 people responded that they used all 3 methods. So we know that there's going to be a 5 right here, okay? That's, again, the intersection point. Then we're going to go up, and I'm going to look at the phone and television section. So first of all, notice where that is on your Venn diagram. Phone and television would be this intersection point, right? I'll shade that in green. Phone and television. So this region has 8 people. Agreed? But here's the thing. 5 of them have already been accounted for here. The entire region has 8. So if the entire region has 8, and we've already accounted for 5, that means if we do a little subtraction, we know that this has to have 3. So do you see how that works? What I want you to do then is see if you can continue this all the way up. See if you can continue that all the way up and fill in the rest of your diagram based on this information. Go ahead and pause and now retry if you need to make changes from what you previously did. So I will keep going. So the next one I'll look at is the computer and television. So that has 12 people. So computer and television is right here. Computer and television. Make sure I'm looking at the right section. It has 12 people. 5 of them are already accounted for, which leaves me 7 over here in that section. Okay. So we've got those 3. We're working our way up. Now we're going to look at computer and phone. Computer and phone. That has 10. Where's computer and phone? Again, that's going to be this little football shape down here. Computer, phone, the intersection. I said that had 10. We already have 5 in there. That leaves another 5 for right down here. How are you doing so far on your own diagram? All right, we've got several numbers left to fill in. So let's look at the television region here. The television said it had 40 total. 40 total. Well, the TV region is all of this, right? All of this section. Well, we already have some in there. So if we take 40 and we subtract, what is 7 plus 5 plus 3? 15. We already have 15 down here. 40 minus 15 leaves us with 25. So we know that 25 people exist up here. They use the TV, but not the computer and the phone. That's what that means. Let's look up in our table one more time. How many use the smartphone? 30. So our smartphone region is down in the bottom right. Again, I think highlighting it is helpful. So here's our smartphone region. I already forgot the number. What was the number? 30. So we've got 30 people in the phone region. We've already accounted for 5, 5, and 3, which is 13. So if we subtract 13, that leaves us with 17 people were only phone, right? 17 people were only phone, no other method. And the last, computer. Computer, 55 people. 55 people surveyed, said they used only the computer. So 55 minus, well, the computer region is all of this. So what do we have? We have an extra 7, 5, and 5, which is 17. 55 minus 17 is 38. Erase my highlighting. 38 goes here. And we've got all of our circles filled in. Fantastic. Are we done? No. Why not? What we've done so far is we've separated. What we've really done is we've taken these numbers and we've sort of separated them into different chunks, right? We know that some of the people who use the TV also use the computer, also use the phone, maybe did both, and we've pulled them apart. And so if we go all the way back to the beginning, we said that 120 people were surveyed. So this entire grouping needs to include 120 people. Let's see what happens if we start to add up all of these different regions. Let me pull up my calculator here. Pull up my calculator. And I'm going to add all of those numbers inside our different regions. We had 25 plus 7 plus 5 plus 3 plus 38 plus 5 plus 17. So I think I got all those accounted for. I'll double check up here. I'll look at my numbers. 25. Whoops. Let's keep the calculator up. 25, 7, 5, 3, 38, 5, 17. That's 100 people. So inside our current diagram, all of these numbers add up to 100. But we should have 120. Well, what does that mean? We've got 20 people left over. Where do they go? They are in our universal set, but they're not inside any of these other sets. So what does that mean? It means they didn't use the TV or the computer or the phone to access their news. And that was what our question was. How many people did not use any of these methods to obtain their news? 20. And we could answer all sorts of questions based on this. The key is to not double count any of the areas, right? I could say how many people used the phone or the TV. How many people used the phone or the TV to access their news? Well, that's a union, right? Phone or TV would be all of these. And we would add all those numbers together. So hopefully what you're seeing there is that Venn diagrams can be really useful for categorizing information and for separating different parts of these sets. Again, I know that there was a lot in all these videos, but hopefully, right, you're seeing how these things are used, Venn diagrams, sets, how they're starting to be useful. Focus on the notation, focus on the terminology.